This was an exceptionally great example, our standard Hilbert matrix example. But again, if you use this in practice, for reasonable, so what you will get with probability 1, you will lose half of the digits at least. If you use Gram matrix, then you are losing half of the digits. So there are some cases where you can sacrifice accuracy for at least half of the digits, because if the matrix is ill-conditioned, you may lose even more. So there are some cases when you can sacrifice accuracy for speed when you can compute Gram matrix in a fast way. So A consists of scalar products between the columns of A, and if A is a structured vector, such that the scalar product can be computed faster, then it might be an option, which is not preferred, but sometimes it is an option. That's the case when you have this principle of your matrix, it goes out there. So this is the first way. This is theoretical. At least you can use it to prove that the decomposition exists. So the second way is the Gram-Schmidt orthogonalization. And this is connected, of course, to the computation of normal basis. So the QR decomposition is a mathematical way of writing down the orthogonalization process. Why? So if you have this Q matrix times R matrix, so Q is upper triangular, which means that if you compute the last vector, it is proportional to the last column. So Gram-Schmidt does it in an opposite way, but so we want to compute, given a sequence of vectors, we want to compute so we want to compute on orthonormal basis, and the Gram-Schmidt again first here in the university. So what we do, we take the first vector, we normalize it, and at least we get one orthonormal. Then we need to compute the second vector, and we just take the second vector from our set, and we need it to be orthogonal to the Q1. If we want it to be orthogonal, we just subtract some coefficient multiplied by Q1, and in order this vector Q2 to be orthogonal to Q1, it should be, this coefficient should be equal to the scalar product between A2 and Q1. This is orthogonal, then we normalize it. And the exact arithmetic, this vector will be still orthogonal to Q1, and that's basically it. And what you do next, you subtract A3 minus all the others, and so on. This is the Gram-Schmidt orthogonalization. And in exact arithmetic, you are guaranteed to get the orthonormal basis. If you know the orthonormal basis, you only need to compute. And also, this process has this triangular form, because Q1 depends on the A1, Q2 depends only on A2 and Q1, which depends only on A1, and so on. So this vector should not be zero. That's sort of a problem of the Gram-Schmidt algorithm. And also, if I remember correctly, with last year we typically had this problem about modified Gram-Schmidt and original Gram-Schmidt. So yeah, so this is the original Gram-Schmidt algorithm. And this is another example of not very stable algorithm. So you may probably guess what would be the problem of this. Yeah, it will lose orthogonality, right? So, okay, you can get zeros, you will define by zeros, maybe. So actually, in fact, the funny story, if you want to orthogonalize two vectors, this is not an easy task. You only have two vectors. If you do this operation, it is not guaranteed that these two vectors will be numerically orthogonal. Maybe you can guess what to do in this case. If you want to orthogonalize two vectors, you do this, and you find out that they are not numerically orthogonal. What to do? Repeat, right. This is called re-orthogonalization. In fact, what you can look at, you can look here at the norm of Q2, and if this norm is much smaller than the norm of the previous vector that we are orthogonalizing, we need to repeat. And there is a theorem, which is a non-trivial theorem, which says we only need to do it twice. So twice is always enough. We do it once, and then we do it the second time. Numerically, we will always get orthonormal vectors. No, you can prove it using the formal model of floating point computations and this then. This is the result of Kahan. It's called Kahan reorthogonalization. And if you use operations like this, there might be cases when you will losing orthogonality, and that is not impractical. I have seen it. Again, if you have some streaming code which has to do SVD many times, and on the millionth matrix it gets that, and then you just get not a number, or lose orthogonality, that's not a pleasant one, but 2 is enough, called Kahan reorthogonalization. So basically what you do, you compute Q2, and then you again re-orthogonalize Q2 against Q1. So you get like twice the error, but then you're guaranteed to it. But still, it's more pathological, but also in this implementation there is also another problem, that you orthogonalize A3 to Q1 and Q2 simultaneously. So this is called classical Gram-Schmidt, and this is numerically unstable algorithm. It's not a pathological case, it's a generic case. Generic case is numerically unstable. Maybe you can guess how to modify this to get the modified Gram-Schmidt, which is numerically stable. You need to modify this line. Ideas? Yeah, you do not iteration, but you orthogonalize first Q3 not to Q1 and Q2 simultaneously, but one by one. A3 to Q1, then A3 to Q2, if we do it one by one. And in this case, it will be modified Gram-Schmidt, which is more or less numerical, but we will have homework. I think, I might be wrong here, but we used to have such problems in the homework. Okay? So, modified version is more or less okay, in fact. Well, basically, it doesn't here. Modified Gram-Schmidt. So instead of this, you update it one by one. So this is an example of a very small modification of the ending, which is an exact arithmetic of the same, but in floating point arithmetic they have entirely different properties. Okay? What's the complexity? The complexity is linear in the long dimension and quadratic in the number of vectors. So if you need to orthogonalize very long vectors, then you have linear complexity, which is nice, but you have quadratic complexity with respect to the number of vectors. So if you have a square matrix, that would be n cubed, and the coefficient there is like 4/3. Again, Gram-Schmidt can lead to loss of orthogonality. Finally, in the practice, of course, we do. Okay, you can use it. There are people doing modified Gram-Schmidt, it's okay. But a more robust way, which we already discussed, is the use of elementary operations. So instead of doing A equal QR, we want to find an orthogonal matrix that brings our matrix into upper triangular form. So So it means it has non-zeros here and zeros everywhere else. So now Q is a square matrix, and R is a rectangular matrix. Although this might look as a different decomposition, this is actually the same decomposition, because if we rewrite this equation, then the columns of Q is A equal Q times this rectangular upper triangular matrix. Then and then we multiply this. The coefficients corresponding to the columns of Q with the number greater than m, they will be 0. So that would be equivalent to taking this non-zero block times the first columns of Q. So this is another, so sometimes QR factorization is formulated as a product of a square matrix times rectangular upper triangular. But again, if n is large, in terms of storage, there is no need to do this. Why do we store the dense n times n matrix if we can store an n times n matrix? Suppose n is median and m is 10, we can easily store the 10 columns and so on. But again, let's find this. So we will never form this matrix Q explicitly in this case, but we will represent it as a product of simpler matrices. And we just store these simpler matrices. So what we do, we take a householder matrix, which is defined just by one vector, and multiply it from the left to make zeros in the first three, in all the elements except the first one. So we need to map the first column of A to something that is proportional to the first column of the identity matrix. So we do that, then we multiply by another matrix, which does not change, which only acts here on this block. So this matrix has the part of the identity matrix here, and then a smaller householder matrix. This is still a unitary matrix, square, but we want to make two zeros here, and these are untouched because of this special structure. So we multiply, make two zeros here, and finally we need the third householder rotation to make zero here. So it's really simple. Implementing this is, 15 minutes of intensive work, or not very intensive work. So you have the product of three orthogonal matrices, and we have brought our matrix into rectangular upper triangle form. The product of orthogonal matrix is an orthogonal matrix. Then, in fact, depending on the application, we can either leave our matrix in this vector form as a product of three rotations, or compute the first three columns of this product. We want to compute the first three columns, we just run them from the product, and then we form the full matrix. How it's typically implemented, if you ever would have chance to program these things in Fortran, so the standard QR subroutine, it actually returns the matrix in a factorized form, and there is a separate method that turns this factorized form into a dense matrix. So in fact, if you only need to apply, you don't need to have to access to the edges. NumPy typically returns already in the dense form. If you run QR, it just returns the matrix. But what it computes there is computes this factorizations. And of course, in real life, we need to use block algorithms. Thus, instead of using the one rotation, we take a union of this rotation into a block, and then use block householder. So the difference is that with the standard is that U is now not a column, but several columns. It's n times k matrix with orthonormal columns, and this is still a unitary matrix. And then you can use block plus the operations for working with. So basically, you somehow combine these several rotations into a big, several reflections into one big reflection. Okay? And then you have to deal with solving the small subproblems and so on. It's sort of mess, but it works very robustly. So, before going into short decomposition, which will be the final part of this lecture, I'd like to mention the case where the initial matrix has this lowering property in the sense that Okay, QR exists for any matrix. So what happens if the matrix is random deficient? If the matrix is random deficient, it means it's not a full polynomial, it can be approximated by a matrix of low rank. So some algorithms will suffer. So Gram-Schmidt will suffer, Halevsky will suffer, modified Gram-Schmidt will survive, Householder method just doesn't care, but you will have, well, the exact arithmetic, you will have zero somewhere on the diagonal of R. But, for example, if you want to determine what is the actual rank of the matrix using this QR factorization. So then, we need to do something that is analogous to the pivoting in the Gaussian elimination. So what is the analog of pivoting in the Gaussian elimination? We may want to select which column we are now orthonormalizing to the current basis. So in this sense, we permute